and computational fluid dynamics writ large. Ilenia, it's yours.
Thank you, Hamdi. Well, thank you everybody for being here. What a pleasure. I just realized that the last time I gave a talk in our own department was in 2021. So I think it's a good time to, kind of give an update. And the reason why I actually chose this title and this topic because I think I wanted to show that some of the theories and methodologies that we actually have developed for years and years in reactive transport in porous media with applications to, geologic porous media, so rocks, could in fact be applied to battery systems. So systems that are very different, and because our department is so heterogeneous, I thought that this could be a great example of how cross-pollination between fields and methodologies can be actually immensely beneficial and help us understand open challenges in fields where maybe do not work a lot, but on the methodological point of view, but also maybe address some of the issues that can be addressed with that specific methodology. So first of all, I would like to, and this is going to be a little intense and dense, but again, this is a methodological talk, so even if you see equations, those are not necessarily the point. I will try to highlight the conceptual structure that we are following in the logic structure. So first of all, just in introduction for people who do not know us, we are part of the multi-scale physics in energy system group. Of course, these are all the students. These are the current students somewhat, but of course, nothing could happen without the present and past students. I will be presenting a lot of work from some of the current students, but also previous students. And really, we work on multi-phase physics for energy applications, where these energy applications essentially involve porous media. Broadly speaking. We look at all kinds of different scales. We go from a very fine scale, so pore scale right there at the top, to larger scale at the bottom, which is the simulation of thermal runaway in battery pack. We develop a lot of methodologies. We look at numerical methods. We use a lot of applied math. Algorithms of different types, ML. We also do a little bit of experiments, and the physics that we are generally most familiar with and we work with a lot, it's of course fluid flow, heat transfer, reactive mass transport, electrochemistry, but we are not limited to that. We tend to be very curious. So before I start, I actually want to start with a quote. You'll understand that I like quotes a lot, but the reason why I bring this up is because scientific falsifiability is really what drives the way we think about problems, multi-scale problems. And I will explain in a second what I mean by that. So we really adopt a deductive empirical falsification over inductive concept of verifiability in logical positivism. And really, this is just to avoid confirmation bias. And so the reason why I say that is because in the following talk, in the talk, I'm going to talk a lot about applicability conditions when we are very obsessed with when models fail, okay? And we come to that with an angle of, with a perspective that if we understand when the models fail, then first of all, we know when we can reliably use them, and then when we cannot, we can develop better models. So it comes from a space of awareness, not necessarily of criticism. I like a lot this piece of writing by Karl Popper. Is a philosopher of science, and in the poverty of historicism, he's a contemporary philosopher, but I think he died. Well, anyway, he says something like this: if we are uncritical, we shall always find what we want. We shall look for and find confirmations, and we shall look away from and not see whatever might be dangerous to our pet theories. In this way, it is only too easy to obtain what appears to be overwhelming evidence in favor of a theory, which, if approached critically, would have been refuted. In order to make the method of selection by elimination work, and to ensure that only the fittest theories survive, their struggle for life must be made severe for them. So now, with that in mind, like what kind of systems we look at. So we are interested in multi-physics and multi-scale systems for the basic reason that they are incredibly interesting and challenging and intriguing because they put enormous strain both on computational resources but also on theoretical model development. Now, I'm sure you know all about this, but essentially what do we mean by multi-physics system? A multi-physics system is a system where you have multiple physics occurring contemporaneously. They can be coupled, non-linear, it doesn't matter. As long as there is the more physics happening, then that's a multi-physics system. A multi-scale system is when these type of physics happen in a system that or take place in a complex heterogeneous environment that can exhibit a hierarchy of scales. Now, the specific type of multi-scale systems that we really look at are porous media. And the reason why this is multi-scale is because you have a characteristic scale, for example, of the pore, which is much, much smaller, for example, than the characteristic size of this device where this is present. It could be the electrode of a battery, it could be, a geologic porous medium, it could be a rock, it could be anything. And we are particularly interested in trying to understand how the physics at the fine scale actually can affect macroscopic behavior. The reason is because generally we do engineering, optimization, design at very large scale, but really what drives, the macroscopic behavior is really the physics at the fine scale. As Hamdi mentioned, porous media occur in very different applications, from geologic porous media to engineered porous media, and these are some of the applications we work on. We of course work in geologic porous media, reactive transport in porous media. We work on batteries because, we know that the electrodes are porous. Also, we have started working on thermal protection systems for re-entry vehicles, for NASA applications. We have an interesting collaboration. This is because, again, part of the thermal protection system is a resin that imbibes actually carbon fiber. So it's a porous medium that has some complexity and then ablates away. So on top of that, we also tend to consider, again, doesn't matter what kind of reactions these are, but we also look at systems that have a lot of reactions. We are interested in that type of complexity as well. And so now, why are lithium-ion batteries multi-scale, multi-physics systems? Well, I know that you have seen this picture in some way or another multiple times, but batteries are inherently multi-physics systems because we know that different physical phenomena happen. There is lithium-ion intercalation, the intercalation reactions, there is diffusion in the electrolyte, in the solid, heat transfer, and so on and so forth. There are also severely multi-scale systems. This is just an example. Even if you restrict your analysis to the continuum regime, so you kind of neglect what happens, at the atomic scale, you already are quite in a big trouble. You have to cover essentially 6 to 7 orders of magnitude in space to go from the electron scale to a Pac scale, and 7 to 10 orders of magnitude in time. Now, this talk is primarily focused on these 3 scales, although we have started working on density functional theory, trying to incorporate density functional theory simulations in this continuum formulation. So maybe in a few years we'll have some updates. Now, what kind of options do we have when we are handling a multi-scale system? Now, again, let's go back to the image of a porous medium. So we have this solid structure, then we have this pore space, and this pore space can be filled with some fluid, and then maybe there is a solid that reacts. Now, one option is to use pore scale models, right? And again, the physics here doesn't matter. This is just conceptual. I'm not talking about batteries yet because the equations are much more complex. So we'll go easy first. So if you start from pore scale models, then let's say you want to model flow, then you would use, for example, a low Reynolds number Stokes equation. And if you have a solid moving along and maybe reacting with the solid-liquid interface, then you would have an advection diffusion equation with this like some kind of boundary condition that represents the flux at the solid-liquid interface. Now, if we want to model exactly the same physics but at a different scale, then we would have to represent the system differently. So there are these continuum scale models. What they do, they essentially represent, they don't distinguish anymore between the solid and the fluid portion, but represent the entire system as an effective continuum. And one intuitive idea behind this is that if you think about a chessboard, it has the black and white squares. Squint your eyes, and then you'll see everything kind of gray, right? So that squinting is the process of coarse graining, right? You represent something that has some discrete nature as an effective continuum. From a mathematical point of view, this leads to different formulations for the same physics. For example, if you want to model momentum transport, then you would use Darcy's law and an advection reaction dispersion equation. There are a few things that are quite critical when you change scales. The first one is that the equations at the continuum scale may actually look different from the structure of the equations at the pore scale, okay? There is no guarantee that they're gonna look the same. For example, in this case, what was a boundary condition in the pore scale equation now becomes a source term. There are other features. The first one is that, of course, pore scale equation solves for the pore scale quantities at specific locations in the pore space, so you would be calculating, you know, the specific value of velocity, pressure, and concentration at a specific location in the pore space, while continuum scale models are equations that are written that govern the evolution of spatially averaged quantities. Okay, so here we have an average velocity, an average pressure, and an average concentration. Okay, and these are spatially averaged over a reference volume. Now, another important aspect is that at the continuum scale, you see effective parameters appearing. Like in Darcy's law, you have permeability, dispersion coefficient, porosity, some, you know, here the effective reaction coefficient is not there, but so you start having these parameters appearing that are defined just as a result of the coarse graining procedure. Why? Intuitively, if you think about porosity, if you look at the pore scale, again, at the chessboard, it's either black or white, right? But if you now smear it all around, then that's when you can define a porosity. The effective parameter implies that you are operating and averaging over a reference volume, okay? We'll come to back to why that's relevant, right? So now, okay, we have two conceptual approaches that we can follow. Now, what are advantages and drawbacks? Now, pore scale models have the significant advantage that they are obtained from first principles, which means that they tend to be more robust from a predictive point of view. So they essentially tend to work and provide good results for a much broader set of parameters, generally, okay? But the disadvantage is that in order to be able to solve for them, you need to know the pore scale geometry everywhere in your computational domain, and that leads to high computational costs. If your system is very large and your characteristic heterogeneity is very small, then your mesh has to be very, very fine, so high computational costs. Continuum scale models is almost, you know, a complement of that. We don't need to know the pore scale geometry everywhere. We just need to know a distribution of effective parameters. Because of that, we can model, you know, these systems as, you know, we don't resolve the heterogeneity effectively, and so we can use larger meshes, and so we have very low computational burden, but they are built on a number of approximations and hypotheses, and therefore they work and are predictive for a smaller range of values, okay? So now, what do we do in our group? So our group is really focused on developing a multi-scale framework that is rigorously derived, ensures a priori accuracy, and is optimally designed for deployment, right? So what does that mean? So essentially, once we are interested in a particular application, then what we generally do is that we perform a physics-based model development. We start from equations at a given scale of interest, depending on the problems that we are looking at. We derive these homogenized or upscaled models at different scales. With these upscaled models, we also derive the applicability conditions of the model itself. So when are these models accurate, as imposed by the theory? And then with these two pieces of information, we can decide how to deploy them. And the deployment should be optimal. Optimal in the sense that it should be predictive, you know, based on, you know, our desired accuracy, but it also should be computationally cheap, right? And that's a tunable aspect. So whenever we think in our group about model development for this type of complex systems, there are three, I don't know if it's a need or a want, but, you know, there are three things that we like to have. The first one is what is controlled accuracy. We really want to make sure that we incorporate the multi-physics and multi-scale aspects correctly. We want to be able theoretically to incorporate realistic complexity, and we want to also have computational efficiency. Generally, we also would like to do this really fast and also be able to transfer between different fields relatively easily. So now what we are going to do today, and let's see how far we go because I already see that I'm late. But so I will spend first some time kind of introducing the framework. And again, this is not specific to batteries, it's very general. So we're going to spend, I think, about 15 minutes explaining the features. And then we're going to apply the framework to two cases. The first one is electrochemical model, essentially the development of multi-scale models for electrochemical transport in batteries. And then let's see how far we get. This never works. It's thermal runaway. Of course, the idea is that, we want to develop those models because they are fast. Now, the first want that I had was accuracy, right? Controlled accuracy. How do we get controlled accuracy when we do scale translation? So the first thing that I would like to point out is where upscaling methods apply. So generally, these are the systems that can be handled, right? So what you have is some kind of fine scale heterogeneity that happens on a small length scale, and then the system of interest is at a much larger scale, let's say L. One parameter that we will indirectly kind of hear a lot about and is super relevant is this epsilon, which represents the ratio between the characteristic size of the heterogeneity and the macroscopic size. And that's called separation of scale parameter. Now, what upscaling methods, again, are mathematical theories, but they have some features that are very valuable. I would argue that feature 2, 3, and 4, they're not necessarily as appreciated as feature 1, but my argument is that they're actually pretty neat. So feature 1 is that these methods allow you to derive effective, equivalent continua model with controlled accuracy, so this homogeneous model. Now, feature 2 is that not only you can derive the equations that hold at the continuum scale, but you can also derive the applicability conditions of that equation as a function of your operating conditions and values of parameters. Feature 3 is that it also gives you a self-consistent way to estimate the effective parameters we discussed in the continuum scale equations. And those can be related to the structure, the microscopic structure that you have. And finally, the fourth feature, and I hope we'll be able to get there, is that inside the same theory, it also provides a way to formally and self-consistently reconstruct pore-scale fields from average quantities. Now, the reason why this is important is because generally when we coarse grain, we lose information. We have something that is very, is very local, and then we coarse grain, we get an average behavior. But sometimes you might want to actually retain some fine scale information because some phenomena may be very local. Degradation mechanism, lithium plating, it's determined by the potential at a specific location inside on the electrode, right? And so having the possibility to reconstruct fine scale fields without having to solve a full pore scale problem is very valuable, especially from a computational perspective. So now let's see what generally upscaling methods do. So again, application, you pick your heterogeneous domain. In this particular case, it's just like a conceptualization of a battery pack. It all starts with defining a volume, a representative elementary volume. Then what you do is that you define an average over that representative elementary volume. Say you are interested in thermal runaway, you want to understand the temperature distribution, so this function, this psi, it's a temperature, right? So you define an averaging operator, and then the general goal is to start from a partial differential equation that can have a general form. So this could be your conservation principle, okay? Start from your fine scale model, okay, what you think is true. You apply the averaging operator, and the goal, very simply, is to write a new equation. But now the new equation contains a priori a different operator, so we don't know, the equation can be different, but it operates on the average of that variable, okay, on the average temperature. Once you have this equation, then you can solve it, and you can essentially obtain a distribution and then make predictions at much larger scales. Of course, there are a number of different methods that can do that. Volume averaging, homogenization theory, thermodynamic constraint averaging. There are a lot more. Effectively, to some extent, most of them are, very much alike. We use homogenization theory for specific technical reasons, which I don't have time to cover. But I will give you a crash course in homogenization theory in one slide. Okay? So what is this thing? What is this thing? So let's say that we have our porous medium, right? Our complex structure, and we want to build an equivalent continuum representation of this system with this theory. What do we have to do? So the first step is that if you have a disordered porous medium, you have to conceptually believe that it can be approximated as a periodic structure. Okay, we can then discuss about how strong this approximation is. Once you have that, you can essentially, this periodic structure, you can identify this periodic unit cell that essentially represents the characteristic length, is of the size of the characteristic length scale of your heterogeneity. Again, we get this separation of scale parameter, epsilon, which is the ratio between the size of the unit cell and the macroscopic domain. After we do that, let's say we start from our pore scale system of equations. Again, the equations in particular here are completely irrelevant. They're just easy. So we start from the pore scale system of equations, and we non-dimensionalize them. So we have some dimensionless numbers that appear. The importance about the presence of numbers is that their order of magnitude will determine in what range of the dynamics you are, okay? So depending on the value of this dimensionless number, essentially you are spanning a different portion of the parameter space, okay? Then, after you have that, you do something, mathematical derivations, you obtain a continuum scale equation for the average of the quantity, right? That equation is valid on an effective continuum. Now, as we mentioned before, essentially if you solve this continuum scale equation on this domain, and then you look, for example, at the value of the solution at the location, this represents an approximation of the average of the pore scale solution when you average it over the unit cell at that same location, okay? Then, of course, the theory also gives you the form of the parameters, okay? So we know everything. One thing that I would like to note is that we have this strange variable. This is called the closure variable that essentially upon which the parameters depend on. And what is the closure variable? Well, the closure variable is something that satisfies itself a boundary value problem and needs to be solved on the unit cell. So this part can be tricky, but essentially conceptually what happens? Let's say that you have your structure at the micro scale, right? And you have derived your closure problem. You solve your closure problem on this periodic unit cell, and you calculate this closure variable. You take this closure variable, you plug it here, and you calculate your effective parameters. You calculate your effective parameters, plug them back in the continuum scale equation, and you have a full, your full equation that now you can solve. What is the advantage of this? The advantage is that, of course, solving this continuum scale equation on that domain is computationally much cheaper than solving the pore scale equation on that heterogeneous domain. And on top of that, you have known errors with applicability conditions, which I will discuss in a second. Now, how do we check the error? So now we made this derivation, we obtained this continuum scale equation, we have a pore scale equation. How do we check that our derivations are correct? So we do it numerically. So the procedure, again, is relatively standard. We essentially simulate the pore scale system on the heterogeneity that we want. Then we apply a moving average and slide it across that domain to calculate this average pore scale simulation. That represents our benchmark solution. So that's the truth. Then we solve the closure problem on the unit cell, calculate the parameters of the effective equation, plug it there, and solve the equations in the same macroscopic domain. So that's the upscaled equation. We compare the two solutions, and what the theory tells us is that these two solutions need to be, the absolute error between these two solutions has to be bounded by a value that is epsilon. I mean, on this we have to believe me, it's part of the math. But essentially, the point is that you can, with the procedure, you can essentially establish a priori the accuracy of these formulations. Now, the second point that I mentioned, so one was the applicability conditions, the other, one was, the accuracy, and the other is applicability conditions. So, in all this derivation, it wasn't clear how I could define whether that equation would be applicable, right? And so, because the derivation is a little tricky and quite detailed, I will give you just an intuitive explanation of where that happens or how that happens. And of course, I can, then point you to, where the derivation is actually done. So, applicability conditions. How do we know when are these things applicable? Now, let's consider again even a simpler case. We have a channel, right, with flow in a channel. We have a solute that reacts with the walls. So at the pore scale, we have this classical equation, is an advection diffusion equation, and then because the walls are reactive, we have some boundary condition applied on the top and bottom of this domain. Again, we define the average. In this case, the average is just the average along the vertical dimension. And then if you apply this averaging operator to the previous equation, you would get continuum scale equations. Derivation are in this paper by Michelic. So again, the continuum scale equation does not have anything surprising. It's one-dimensional in space because we have integrated y away. It is an equation for the average concentration. It contains effective parameters. But now let's focus on this effective parameter. This is the effective reaction rate when we coarse grain. So this effective parameter K depends on the pore scale reaction rate, which is expected, of course, on the properties of the topology of the fracture, and it depends on this Damn-Collar number. Now, Damn-Collar number is something that tells you how fast the reaction is relative to diffusion, effectively. So, one interesting point that you can make is that, okay, let's assume that for some reason, the reactivity of my wall increases, right? So K increases, maybe temperature is increasing, whatever, something. So the physics is not changing, just the kinetic is changing. I'm reacting faster. So if I increase K at the pore scale, then Damn-Collar number increases, which is fine. But then, okay, Damn-Collar number increases, but when Damn-Collar becomes greater than 3, K changes sign, which means that this term switches from a source to a sink or vice versa, which is of course wrong because we are not changing anything in the pore scale physics. Everything is the same exactly. We are just making the reaction faster. So what's the problem here? Well, the problem is precisely that these continuum scale equations have some hypotheses, and these hypotheses are really related to the magnitude of Damn-Collar number. So if Damn-Collar number is greater than 3, this equation does not represent accurately pore scale processes anymore. But why is that? What is the physics behind it? Well, intuitively, actually, it's just related to mass transport limitation. So if Damn-Collar number is very large, it means that reactions is much faster than diffusion. So if reaction is much faster than diffusion, then what we're going to find at the pore scale are very sharp concentration gradients. Now, when we want to represent a field with an average, essentially, but if we have a field or a very sharp concentration gradient and our variable changes a lot and we want to replace it with a constant, we are not making a good approximation. And that's what it is. So essentially, these continuum scale equations is valid only when you really do not have mass transport limitation and when essentially your diffusion is fast enough to homogenize things at the pore scale. Now, of course, we could show that this could be generalized to more complex systems. In general, effectively, what you can do is that you can derive your effective parameters and then describe this applicability condition in a parameter space where, let's say, if you are inside a general region, then you know that your model works well. And if you are outside, you can't guarantee that anymore. So that's feature number 2. Feature number 3, goes back to the closure problem and how the closure problem is related to the parameters. We know that the parameters in the effective continuum equation can be calculated as a function of the closure variable. So if you were to generate a number of different complex topologies, you can just incorporate this information in your parameters directly, because you would solve your closure problem in any topology you want that you take maybe from an XCT scan, and then you can plug it in and have your effective parameter. The fourth and last is the reconstruction. Now, again, I cannot go into the details, but the general concept is that because all these methods are based on asymptotic expansions, essentially you can use the formulation of your solution to reconstruct an approximate, an approximate version of your Poor scale field. Essentially, you can reconstruct a part of this infinite expansion. It's just a truncation of it. And what you need really to do this local scale reconstruction is the closure variable and your macroscopic field. Once you have these two pieces of information, you can do a downscaling and effectively reconstruct your quantities. So this was a lot probably, and I talked only about the advantages and different aspects, but I kind of hid what the disadvantages are. So the problem is is what I didn't show. And what I didn't show was that behind this arrow, the mathematical derivations of this type of, in this type of situations can be very, very time consuming. They are tricky. And the larger the system becomes, the more complex it becomes, they really become intractable. Another aspect, another open question that we kept wondering about is really, okay, when things, are we now stuck with like toy problems forever? Can we handle complexity? And can we use this method for control? So now, finally, with this premise, which was very long, let's go back to batteries. So I would like to, so all this was developed in the context of geologic porous media, okay, reactive transport and things like that. Then the question is, how did this whole thing about batteries start? Well, it started like this, and unfortunately, I don't see Simone in the audience, but essentially we were both at Clemson in 2013, and I think here we were at a football game. And so we had just joined and we started talking, and she was doing control and I was doing multi-scale modeling. And so it became immediately clear once she described a little bit how these batteries worked and that there was a porous electrode. I said, oh yeah, that's gonna work. It is gonna work. And so she invited me back then she was at ICAR in 2014, where I gave like this talk. Of course, it was just a general outline of how the entire pieces of the logic would work together. And so, well, what is a battery? Again, this is fast, you all know. This is a rechargeable device. The lithium ion moves between two solid electrodes through the liquid electrolyte, okay? These animations, by the way, are by, one of my previous VSR they're quite amazing, so I had to include them. So the idea is essentially what happens is that the lithium ion intercalates and they intercalate from one side to the other side and travels through the electrolyte. So from a modeling perspective, this is essentially a reactive transport problem, okay? So what were the approaches that were generally used? Again, here we are in 2013, so many years ago. So there were, conceptually defined scale methods, right? But again, there was really no solver. And the Nernst-Planck-Poisson equations. Again, the reason why I include them here is not because we have to, understand them. It's because effectively what we need to know is that in each electrode, we have the electrode particles and we have the electrolyte. In each of these two domains, essentially, we have two sets of equations that are holding. One is an equation that represents balance of charge, and one is an equation that represents mass balance, okay, of concentration. And so for this reason, you have two equations in the electrolyte domain, two equations in the electrode domain, and then there is a boundary conditions that essentially regulates how quickly the lithium intercalate of the intercalates. And it's a little messy because it's not linear, there is a lot happening. Now, of course, at that time, specifically for control application, this is not happening. It's a non-happening situation. But there was, from the physics-based perspective, there was a much interest in P2D models. Again, we are in 2013, or also known as DFN model. Now, these models represented a very good compromise, and people were getting very interested in it because they had a good trade-off between accuracy and computational cost. And there is a lot of research in it, and they were excellent for design and optimization at the larger cell scale. Now, again, regardless of the equations, conceptually, the way these models work is that this is called the pseudo two-dimensional model because there is a macroscopic coordinate x that goes across the two electrodes and the separator, and essentially represents and models transport in the electrolyte. And then at each point in this macroscopic dimension, then there is a pseudo dimension, which is the radial dimension representing transport in a spherical particle. So fundamentally, this model is some kind of a hybrid. It's a coupled macro scale, micro scale, because at each location you are effectively solving contemporaneously also transport in the solid particle. Okay, and so this was really the state of the art. And it was great, working really well, but it had a number of limitations. So the first one is that it assumed spherical particles and therefore cannot account for local heterogeneity. And we know that, not in our best dreams even, the electrode particles of a battery are in fact spherical, although sometimes they are spheroidal. The second one was that it was fast for design, but not necessarily for real time. Maybe at this point in time with AI, this is less of a concern, but the inline monitoring was complicated. The most important concern that I think at the time was that the predictive performance of the P2D model degraded for varying operating conditions, okay, for different temperature and C rates, in ways that were to some extent, I would argue, unpredictable, in the sense that there was no formal way to derive or understand or account for these discrepancies. There were generalizations, but then sometimes they worked and sometimes they didn't work. So there was not like a coherent approach to overcome certain model-based limitations. And so at that time we started actually with the middle, right, with the middle problem. And this is actually a Rikesh. This is again, we go back to 2013, 2015, so quite some time ago. He was a student of Simone at the time, and he was put on the very difficult task of actually learning homogenization theory by multiple scale expansion and essentially applying it to the Nernst-Planck-Poisson equations, okay? And so he spent, poor thing, like days and days and days in my office. So, and that's what he did, and he did it beautifully. So he started from, again, the Nernst-Planck-Poisson equations that you saw before, and then homogenized them to obtain the equivalent continuum representation. Again, I remind you that because there are the electrode domain and the electrolyte domain, we will build, this approach always builds an equivalent continuum for each domain in which you have transport. So this is like a dual continuum, right? Because you have an electrode equivalent continuum and electrolyte equivalent continuum. And then, of course, they are coupled. Again, the point is not looking at the ugly equations, but the fact that he also followed through the entire strategy, could calculate, of course, the effective parameters, the closure problems, the applicability conditions of these models, which I just briefly discussed because I'm limited in time. And with the applicability conditions, we started looking actually, if there was a way to predict which kind of chemistry would actually, for which kind of chemistry these models would not work. And the applicability condition is whatever falls inside the colorful region is good. If it's outside, you lose predictivity, or better, you don't know whether it's going to work or not, okay? So these are just sufficient conditions, not necessary. And so what he found was that essentially, depending on the chemistry, these models could either be very good or maybe not. And the reason was precisely related to the mass transport limitations. So the chemistry really governed the interplay between diffusion and reactions, and that interplay, it was what governed essentially the creation of mass transport limitations at the Poor scale. He also essentially elucidated why there was C-rate induced model failure. So one thing that started being observed quite extensively in those years is that as you increase C-rates, these models performed worse and worse. Essentially, he demonstrated mathematically that this was related to the strong dependence of the parameters of the electrolyte and the electrode to temperature. And because the parameters changed, the transport mechanism changed. And what was not mass transport limited at a given temperature became mass transport limited at a higher temperature. And that was more likely to happen at IC rates. And he did all this by hand, okay? So great, Arikesh. Now later, so by then we had learned a few things, the things that I've said, I'm gonna move on. And so we, were quite satisfied. Still, this had not been addressed. And so later when I joined here, essentially I started working with Ross, who graduated, on seeing whether we could incorporate complex topology. And essentially, one of the issues with the P2D model was also its parametrization. Very often the Bridgman relationship was used, and this Bridgman relationship simply says that the effective parameter in the P2D model is related to the Poor scale property through porosity to a given power, okay? So it was a very simple conceptualization, which had a few limitations. More importantly, could not account for anisotropy and in any of the of the transport parameters, and was highly inaccurate for complex morphology. So even if you took something that was as simple as the image, essentially the difference between the effective parameters in one direction versus another was significant, and of course Bridgman could not capture that. And so what Ross did was to say, okay, he came up with this idea of combining homogenization theory with convolutional neural networks. And so what he did was he generated essentially synthetic structures, 100,000 periodic unit cells, which span the large values of porosity and specific surface areas. Then at step 2, he solved the closure problem in each one of them and calculated the effective parameters of the macroscopic equation in full tensorial form. He trained on this data set the CNN, and then essentially deployed the CNN for validation. And the match was really good. So this was the CNN prediction on a synthetic data set. Bridgman with different fitting method, was clearly not as good. But the important thing that, what we found even more interesting was that the CNN was practically as fast as a Bridgman evaluation, which gave us hope that we could use this probably in a control system. We also used validation against, realistic images in 2 dimensions, and also realistic 3D structures. So it performed very well. So by then, essentially, we had seen that also that aspect could be addressed with this framework. And finally, the question remained of whether this entire thing could actually work for control. And that's, there was another step before we could address that aspect, though. as of that, like as of, maybe a year ago, we really had not formally validated the homogenization model. We have not done a rigorous error analysis. And so this was actually done by Alessio, who was a VSR for quite some time here in the department, where essentially he developed the pore scale model, the homogenized model, and then made sure that the error, was satisfied. I would like to point out that the computational cost or time was dramatically different between pore scale and the homogenized model, and even the homogenized model ran faster than the P2D. So with that information, now we were kind of confident that the model was good enough to be deployed. And so that's when Alessio came, and he was interested in actually trying to implement some of these strategies for control. And so in particular, he was interested in health-aware smart charging protocols for fast charging. And the reason behind that was that essentially you want to develop protocols that prevent lithium plating. And you can do that by making sure that at the pore scale you don't reach a potential that is lower than 0 volt versus lithium plus. So we needed to have some kind of virtual local sensor that the model became. And so what Alessio did was essentially to use this downscaling strategy, this reconstruction strategy, to reconstruct the potential at the fine scale, and then to implement this in a control algorithm. And I think I'm also run out of time. So yeah, with that, we were kind of happy. I think the second part, which I will not have time to cover, really is concerned with thermal runaway, which is something that we started working on around 2020, and became a problem. I really wanted to show this one. But I think I may stop here. I will probably maybe say something quickly about complexity. Before concluding, because I had mentioned numerical and symbolic computing. Now, I did mention. Oh, oops.
It's coming.
Oh, it's coming. It's dead. Oops. Oh, I did something unforgivable.